Hi everyone, thank you for coming. Today we'll be talking about RabbitMQ and Raft and the future of RabbitMQ a little bit. My name is Michael, I'm a staff engineer at Pivotal on the RabbitMQ team.
My name is Karl, I'm also an engineer on the RabbitMQ team.
Before we say anything else, here's a wall of text that basically says don't base any purchasing decisions on the contents of the stock. In fact, don't believe anything you see, and it's all like a dream and may or may not materialize as a feature in RabbitMQ at some point. You have been warned. So before we start talking about the future of RabbitMQ, let's briefly cover what it is. So it's a messaging broker, right? What exactly does that mean? You have apps that are publishers, and you have apps that are consumers. Of course, an app can be both, but we can demonstrate it like this. And you have this middleware layer that does authorization, routing, storing things on disk, delivering to consumers, handling redeliveries, and so on. So that's what RabbitMQ does. It's a data service. It's a piece of middleware. It supports multiple protocols. It has been around for basically a decade, and as any project that has been around for a decade, it has some things that it gets right and some things that it doesn't get right. We will mostly focus on the latter part today. It has a fairly broad ecosystem, including Spring support, and you can learn more at rabbitmq.com. One thing that is very important to mention before we talk about anything else is that RabbitMQ nodes can be clustered, and there are basically two primary reasons for doing that. One is partitioning your workload between nodes, but also tolerating node failures, in particular by replicating queue contents. So today we'll cover where we are with the high availability story in RabbitMQ and why it's not as great as we would like it to be. We will cover Raft and what it is, how we are going to adopt it, at least what our current thinking is. Then what it takes to adopt and implement Raft, because definitely there are downsides and question marks, as with any distributed systems algorithm. Okay, so with that, let's take a look. Where are we at the moment?
Okay. So like any good data service, RabbitMQ has got a high availability story. And achieving high availability typically necessitates the need to replicate your data and replicate your operations. And RabbitMQ does this. RabbitMQ does it at the queue level. So a queue is a primitive in RabbitMQ. We call this queue mirroring. So we got a master queue, and we got one or more mirror queues on other RabbitMQ nodes, RabbitMQ cluster nodes. And the reason we have this is for failover and redundancy. Right? Try to keep your data safe. Now, the RabbitMQ HA story isn't perfect. I hope that's not a complete shock. I think we are in good company. There are many other data services whose story isn't perfect either, but the only one that we can affect is our own, and that's what we're trying to do. We're quite happy to be open about this. Internally, RabbitMQ uses a component named guaranteed multicast. And that's used to replicate queue operations and message data. Now, when you decide to name something guaranteed anything, the question is, what is guaranteed? I think the only thing that's guaranteed is probably it's guaranteed to disappoint at some point in your operational life. And we've had a few disappointments around this. It does provide replication, and importantly, it does provide us with a total order operations on all our replication nodes. And ordering is very important. So if you take a very simplistic queue-based set of operations, an NQ, another NQ, and a DQ, if you reorder those operations, you may not necessarily end up with the same end result state. So ordering matters. So the guaranteed multicast implementation is very much either based on or just accidentally similar to a replication approach called chain replication, which was published in 2004. There's a paper there you can read a little bit more about. how does chain replication work? It works a little bit like this. It's actually relatively simple, which makes it attractive from an implementer's point of view. So you organize your nodes, whatever your nodes are, it doesn't really matter in this instance, as a chain. So you've got a head and you've got a tail. Whenever you've got an operation, say you want to write something to like a key value store type of application, you write it to the head then passes it down to its nearest neighbor, who passes it along to its nearest neighbor downstream, and then until it reaches the tail. When you want to read something, you read from the tail. And whatever you read from the tail, you know that the result has been fully replicated across all nodes, so it's consistent. And if you want like a dirtier read, you can read higher up the chain if you choose to. You can read from the master to get the very, very latest data that is coming through. RabbitMQ mirrored queues, as I mentioned, take a similar approach. We call the various actors in this masters and mirrors. And it's not a chain. Instead, it's a chain that wraps around where the tail is also the head or the master node. So in more kind of RabbitMQ messaging domain terms, if we publish to the master, the publish operation will pass down all the mirrors until it reaches the last mirror. We will pass it back to the master. And then the master knows everyone's seen it, and it knows it can deliver it if there is a waiting consumer. And then failure happens. Inevitably, failure happens. I mean, if we wouldn't be doing any of this if there were no failure events. In this instance, one of the mirrors has failed. So if you look at the topology now, you can see that there's no way we can make progress with a failed node. So we need to detect the node. So we need to detect the node in a timely manner as well. Otherwise, we'll have a potential outage. When we do detect this node, RabbitMQ Mirrored Queues reforms a ring without a failing node. And that's how we regain continuity of service. This node can keep going, does publishes, deliveries, and all that stuff. Now, what if it wasn't like a hard failure? What if it just crashed and then started up very quickly again? Or maybe it didn't crash at all. Maybe there was a network partition event, or it just went particularly slow. Typically, failure detection is based on timeout, so there are many ways you can achieve that timeout. So it comes back, and it wants to rejoin. Now, it was only gone a while, but the other mirrors might have moved on. They might have a whole new set of operations that this node now hasn't seen because it hasn't been involved in the ring. And the master says, it's complicated. It wants to rejoin, it's complicated. The reason it's complicated because we now have to do a synchronization from master to ensure that the mirror that was gone for a little while, maybe it didn't even crash, now receives all those operations that it didn't have before, all the messages that it missed. And in fact, it's a little bit more primitive than that in real life. The downside of this synchronization operation is that whilst it's synchronizing this mirror, it can't actually make normal transactional progress. It has to wait until it's finished with that, and then the queue is active again. So that's a downside. Regarding ring topologies, I was browsing our very own documentation not so long ago, and found this little gem in the documentation about federation. Federation is a means by where you can connect independent RabbitMQ instances over longer distances than clustering supports, for example, over a WAN connection using the AMQP protocol. And here we are stating for our users that ring topologies can be rather fragile, and that's true. So it's certainly a case of where you should do as we say, maybe not as we do. That said, RabbitMQ Queue mirroring works well most of the time. It's reasonably performant, it's simple, it's relatively easy to reason about. But it does require good failure detection to to regain that availability. And membership changes are expensive because they require this synchronization operation, which is expensive. And we haven't covered this, but if the master fails, the algorithm for selecting the next master is informally specified at best. We feel that we can do a lot better than this. So now I'm going to let Michael talk about the road to Raft.
Right. Thank you, Karl. So now that we know where we are, let's take a look at what do we need. Historically, RabbitMQ, in fact, most messaging technologies have been consistency-oriented. We have explored designs that would make it an availability-oriented or eventually consistent, if you will, system, and we just come to the conclusion that's not the kind of system that our users expect. And yeah, so we need strong consistency. So for example, we need total order of operations. We need predictable behavior in response to failure events, or well-defined recovery procedure, if you will, or as our users would explain it, a safer queue master failover. Another thing about chain replications, if you take a look at the way it is visualized, you may notice that it's a linear algorithm. And we all know how well those scale with respect to the number of nodes in this case. So we'd like to have something that does parallel replication. And last but not least, we would like to avoid reinventing yet another distributed systems algorithm. Our team historically has done that a couple of times. More often than not, you get it wrong, and yeah. So if you hear someone suggesting, hey, let's invent a new distributed system algorithm, stop, take a deep breath, do some research, and almost certainly you will find something from the 70s, 80s, 90s, maybe even this century, that is kind of sort of similar to a case or does exactly what you need. And it has been verified, peer-reviewed by PhDs, and all that. So don't do that. It doesn't work very well. It can be really, really costly, speaking from experience. So what options do we have? So we already ruled out chain replication because we definitely don't need more of the same. So there are three major papers or algorithms in this space. So one is Paxos. Originally, Paxos, what is called the single decree Paxos today, was a fairly small in scope kind of paper and algorithm, and it was explained using interesting parallels with Greek democracy and such, which unfortunately gives it a certain reputation, which I don't think it necessarily deserves, but Paxos has, it's not a single algorithm anymore. It's an algorithm and dozens, and seriously, it is dozens, of flavors that fill in the blanks that exist in the original paper. So Paxos has a serious fragmentation problem. It certainly can be used. In fact, a couple of data services, Cassandra and React 2, adopted it in some areas of the system, and it works well for them. But Paxos is not a no-brainer if you ask our team. Next thing is view-stamped replication, an algorithm similar to Raft, which we'll talk about later. It was developed by Barbara Lisko, and it's a fairly small thing. It has the opposite problem. It's actually pretty difficult to find it used, implemented, and evaluated in the industry. So it doesn't have the fragmentation problem. It's just not used all that much, outside of academia at least. So again, it's not necessarily a no-brainer. And a few years ago, a new algorithm appeared in this space called Raft, which tries to be, have fewer blanks that implementers have to fill. So it is implementer-oriented. And it tries to cater to system implementers in a variety of ways. So what is Raft? It's a group of algorithms that collectively help you reach consensus in a distributed system where nodes can fail. If you take a look at the paper, it covers a very similar problem space to at least RabbitMQ Queue Mirror and some other parts as well. Like I said, it tries to be implementer-friendly. And by now it is proven. And by proven, I don't just mean that it has a temporal logic specification that machines can verify. There are multiple implementations of Raft out there in data services that, in fact, you may be already using or exploring. Sometimes as different as etcd and CockroachDB. They have very different systems, and it works pretty well for them. And last but not least, Raft does not require an external tool or network of nodes to be present for you to use it. So basically, it can be implemented as a library, which is a very, very desirable characteristic for RabbitMQ because that's how it works today. It doesn't have external dependencies, well, other than the runtime. So Raft provides, Raft is built around an abstraction of a state machine transitions log, right? It's something that you typically find in data store and so on, but it actually can be applied to a variety of domains. So your web app probably doesn't work like this, but it could. You have an initial state, something happens, the state machine transitions, something else happens, it transitions again, and you have your final state, or at least the point in time state. So it fits many domains. It uses a leader-follower model. Basically, all operations are applied to the leader, then replicated to followers. It includes leader election. And yeah, it is consistency-oriented, and it guarantees total order of operation because, well, all operations go through the leader, right? It covers a number of areas that are not very interesting to academia, but are crucially important to those who implement, who adopt Raft. Like, okay, how do you perform leader election, especially when you first form a cluster where there is a natural rest condition between nodes? What happens when cluster membership changes? You need to add a node, or you need to decommission a node or replace it, because that definitely happens in day 2 operations. You probably want to store your data on disk, so okay, what kind of expectations should your system have? Also covered in the Raft paper. Recovery, if a new node joins, how do you propagate the log to it? How do you do snapshotting, which is important for implementing backups, right? All of those things, each of them is not necessarily an interesting problem for academia, but they are collectively very, very important to implementers. So how does Raft work? We're only going to cover this leader-follower model. So leader election at this point has already happened. So we have a cluster of 3 nodes. We have a leader, and we have 2 followers. And we're applying this operation in queue message A to the leader. The leader has a bit of state and commit index, which I'm going to describe in a bit. So yeah, we have a log which has this one operation. The leader broadcasts it to followers in parallel, which is what we want. At some point, those followers store it on disk or on any other durable storage and communicate back. Like here, we have one follower which confirmed to the leader that, hey, this has been stored on disk. So now we have 2 out of 3 nodes who stored this log entry on disk, right? So we have consensus because the majority, the majority agrees sort of on the state of the system at this point in time, which means the leader can modify its state, assume that this operation was successfully committed, increment its commit index, which is used to keep track, like up to what point have we successfully replicated committed operations, and then respond back to a client with success. Note that follower 2 may be lagging behind, but it's not required at this point for the leader to wait for it before it can confirm an operation. So it is asynchronous, safe, and parallel. 3 things that you probably want in your data service. So you can learn more at raft.github.io. They have nice infographics. The paper is fairly approachable, if you ask me. And yeah. So how does Raft compare in terms of error handling, for example, to what RabbitMQ does today?
Thank you. Right, OK. So I wanted to talk a little bit about what distributed systems do, or their approach to when there is a failure or when a potential failure might be detected. So there's a few strategies you can take on. The simplest one is to do nothing. So it's also the most reliable one. If you've got a distributed system, many different nodes, and one fail and the other ones just don't care, they're able to continue without it, that's kind of the most reliable system that you could probably design. Now, it's very hard to design a useful system from this principle only, but yeah, that's kind of where you want to be. An alternative to that is to try to fix stuff. You know, a failure is detected, or a potential failure, and everyone tries to kind of fix the issue, try to evict down nodes, maybe reform topologies, communicate changes to other nodes. Everyone gets busy trying to help out. And there's kind of like an intermediary choice where you try to do something, but whatever you do, it's a minimum, absolute minimum that you can do in order to try to regain and retain availability and consistency. So with that in mind, we can compare how Raft handles a follower failure compared with how RabbitMQ Queue Mirroring handles a mirror failure. So Raft does nothing, because as long as Raft has got a quorum node available and responding, it will continue to commit entries and progress will be made. So in this instance, it's doing A, it's working fine. Compare that to RabbitMQ Queue Mirroring, whereby it has to do something. It has to detect that failure, and it has to reform that ring. So it does have to do that. And whenever you have to do something, the chances of you doing something suboptimally or wrong is a lot higher than when you're doing nothing. I'm not advocating laziness, but yeah. And in the case of a leader failure, both sides do have to do something here. So Raft, in Raft, a leader retains his leadership by continuously communicating to the follower that it is a leader and it has this log. So it keeps sending messages to the followers. If it stops sending those messages, one of the followers may time out. And when it times out, what it will do then is initiate an election procedure whereby it asks all the other followers whether should I take over as a leader, it asks. And if its log, and this is crucially important, if its log is up to date and has got the latest entries, then it will be elected leader and it will take over and continue and progress will be made. Now, Queue mirroring uses a similar approach. It will detect the failure, it will reform the ring, and the mirror with the longest uptime will be promoted to the master. So the crucial difference there is that it doesn't actually take its current data state into account in the election procedure. So in response to a potential failure of Raft, either does nothing or it does the minimum required so they can ensure consistency of the data and regain availability in terms of processing. RabbitMQ Queue Mirroring must always do something. Okay, so Michael, adopting Raft.
Thank you, Karl. So now that we know the difference in a few areas, such as failure handling and parallelism, let's take a look at how we can use Raft in RabbitMQ. We have been working on this for maybe 9 to 10 months. We realized that there are multiple different areas in RabbitMQ which can benefit from Raft. They don't have to all release at the same time, so we can adopt it incrementally, which is a very good thing. Obviously, our area of interest or focus is queue mirroring first and foremost, but there are several problems that come down to coordination and leader election in RabbitMQ. So for example, we have plugins such as Federation and Shovel, which connect independent nodes or clusters. And you need to maintain a set of connections between them. And you don't want to have duplicate connections, but you also don't want, in case of a node failure, to end up with a connection that is never recovered. We have a delayed message exchange plugin and parts of MQTT where message publishing can be delayed or retried. And you want one part of the system doing that. You don't want duplicates again. And you want that part to have access to all the same, a consistent data set of things to publish. So that's another area. If we dig deeper, we can change our message store data replication algorithm to use Raft, to be based on Raft. So we will be replicating messages as opposed to queue contents, or we can do both. Lastly, RabbitMQ has internal metadata store, data store, if you will, which stores your vhost, users, permissions, queues, and so on, basically everything that's with messages. It has certain characteristics. It was designed for certain workloads that are not really optimal for RabbitMQ. It can be replaced with a Raft-based store as well. But those latter two things are currently in the research stage. So what would that give them, give the user? So as we already discussed, more predictable recovery from node failures is one thing. Improved serializability and it also possibly linearizability characteristics, which basically means there are certain distributed system tests, Jepson being the most well-known one, that Rabbit may or may not pass today, but will be able to pass more of them, maybe all of them, at least a subset, in the future. It definitely becomes more feasible. Better scalability of mirrored queues with respect to the number of nodes due to parallel replication. And because Raft is based around this idea of a log of operations, you effectively adopt another thing that is missing in RabbitMQ, just not, it's not related to mirroring really, called write-ahead log, which most data stores use, and it's not a new concept, and it helps nodes to, if they fail before they commit an operation locally, they then can recover and replay at least some of those operations from disk, which opens the door for incremental backups and multi-data center support, because replicating the log, again, it has been done before in many, many services, and it works decently. So those two things, they don't come for free just out of adopting Raft, but Raft effectively opens the door for them because you cannot not have a write-ahead log with Raft. So now let's dig deeper into some of the more intricate aspects of where RabbitMQ can use Raft.
Thank you. Yes, so down the rabbit hole is a good title for the next section. It's Michael mentioned message store replication. So when you start iterating on and designing these things, you get new ideas. Maybe replication at the queue level isn't always ideal. Maybe we should do it at a lower level, at the message store level. So what benefit could we gain from that? So RabbitMQ allows for very complex routing of messages. So a single message that you publish to an exchange could be routed to many, many queues in a fan-out type of pattern, which means that that message will be copied all over the system. Which results in many consumers receiving the same message body that was copied to many, many queues. Consumers could be connected to any RabbitMQ node in a RabbitMQ cluster, but queue masters may only exist on they may exist on any RabbitMQ node. It might not be the one local to a consumer that they're currently serving. So they might need to cross the network in order to deliver this message. And if there are multiple consumers there, they might cross the network multiple times with effectively the same message, even though it's residing in different queues. A kind of an effect of replication at the queue level. So the gain we could get from replication at the message store level is, reduce this suboptimal use of the network and sending the same message multiple times. So if we replicate the message bodies independently of queue operations, so we still need to have queue operations because we still have queues, and these queues have logic. They need to keep track of which consumers are currently interested in messages and where they're at in the log and what the state of certain in-flight messages is. But the messages themselves don't contain this logic. They're pretty dumb. It's binary data that you need to push around. So maybe using our learnings from Raft, maybe we could design something based on some subset of the Raft algorithms to replicate message data across a cluster. And whenever a consumer needs to consume a message, it gets a pointer from the queue to something that is stored and replicated and available in their local message store. So we're avoiding crossing the network unnecessarily, and I think we can, get some great benefits from that. At least at the moment, it's only a theoretical thing, but in practice, it should play out. Implementing and using Raft doesn't come completely without its challenges. There is an inherent cost to achieving consensus. Raft and Paxos require stable storage. And by stable storage, effectively these days, we mean we need to f-sync an entry to disk before we can proceed. And that has a latency implication. We can get good throughput, but latency is something that we have to trade off if we want this additional consistency and guarantees. Counterintuitively, it could result in reduced availability, because at the moment, a RabbitMQ cluster could shrink quite happily down to a single node. With Raft, we always require a quorum, so you have to be careful with the number of nodes that you stand up. Cluster formation, Raft cluster formation might require some care. Typically, if you grow a Raft cluster from a single node up into multiple nodes, there's timing to take into account, and you may end up with a split cluster. We can probably mitigate those concerns with initially seeding cluster formation with all the nodes that they need to know about. But we're hoping that this will be a RabbitMQ internal concern and nothing that operators need to worry too much about. And in addition to that, the single leader has scalability implications, because all operations need to go through this single leader. I mean, that's no different from the way queues work in RabbitMQ today. And we always try to hammer home the same message, that the queue is the unit of parallelism in RabbitMQ. And if you want more parallelism, more throughput, you need to have multiple queues. You can't just put everything through a single queue. It only scales so far. And that's certainly still going to be the case. There are some operational changes. I already touched on them really. With Raft internally in RabbitMQ, we will need clusters to be of an uneven number. It's relatively simple to reason about that because you need a quorum. So if you've got a 3-node cluster, you can tolerate 1 failure. If you've got a 5-node cluster, you can tolerate 2 failures and so on. If you've got a 4-node cluster, you still can only tolerate 1 failure. So even cluster sizes just don't make sense. So might as well not support them. Right, over to Michael for a little announcement.
So we have been working on Raft adoption for 9 or 10 months, and what do we have to show so far? So we have implemented a Raft library. It's a mostly complete Raft implementation by our team. It will be open sourced later today. It is Apache 2 or MPL 1.1 licensed. It is generally usable, meaning it's not tied to RabbitMQ. You can use it in any Erlang or Elixir application. But of course, it is heavily inspired by RabbitMQ needs. It's still very much a work in progress, so we expect breaking API changes, some internal changes, especially in the persistence area. So yeah, don't maybe bet the future of your company on it just yet, but you will be able to find it on GitHub with some design, reasoning, and so on later today. So now let's discuss certain implementation details and design choices we had to make, given that we have to bridge Raft with its pros and cons and RabbitMQ with its needs.
That's right. So what we wanted to do, we wanted to use this Raft cluster to mirror a single queue. So Rabbit has many, many queues, typically. A Rabbit installation will have many, many queues. So that means many, many Raft clusters. So initially, we implemented Raft in the standard way, following the paper. So every Raft cluster has got its own log, and so that will result in a log file on disk. And we tested that, and we ramped up to, I think I've tried 1,000 clusters, and all those concurrent f-sync operations basically killed it completely. It burned. So we tried that. That didn't work. Another thing we noticed during this test was even if you had like an idle number of Raft clusters running, it's very chatty. So the network usage is quite high. The reason for this is that the leaders continuously try to keep their followers in check. And when you got thousands of these, then that does all add up. So we wanted to address all those in our own implementation. So the way we've addressed the disk contention issue is by having a shared write-ahead log that all Raft nodes inside a RabbitMQ or Erlang node write to. This f-syncs in batches, so it writes a bunch of entries and f-syncs. And then periodically it will flush all these entries that were written to a Raft node-specific storage, which is read-only. So we effectively had to write our own storage engine that's tailored towards our own very specific RabbitMQ needs. It's very similar to prior art, such as to log-structured merge tree storage engines, such as LevelDB and RocksDB. We've made the compaction story a lot simpler by basically not doing any compaction. We just truncate, because we can do that because of the domain that we're storing, log entries. We've also, rather than having leaders continuously keeping their followers in check, we have them go quiet, and instead we have like a RabbitMQ node central heartbeating process that heartbeats with the other RabbitMQ nodes in order to potentially detect things like network partitions and then hint back to the Raft nodes running on the cluster that, maybe you should start an election now, rather than each Raft node making that decision on their own. And this all working reasonably well. We tested this. We can get good throughput and a good scalability in terms of the number of nodes. Right, Michael, you want to cover this?
So because implementing Raft is not really something that you can do in a couple of evenings, right, or over a long weekend, it's important to consider how do you test this. In particular, because we had to deviate from the vanilla Raft, the actual paper, a little bit here and there to make things more efficient. So, of course, we have, your good old unit and integration tests, but honestly, that's not really sufficient. So we're working on primarily property-based test suite. For those of you who are not familiar with property-based testing, it's also known as generative testing. Basically, you tell a library a set of rules, and it generates a lot of test cases for you. By a lot, I mean it can be millions or more if you need to. And of course, it's a lot more extensive if you get it right in integration testing, because a developer, even a very good one, can only write so many test cases in a month. And a machine can execute millions, generate and execute millions in a fraction of the time. And all of this is because correctness for something like Raft is, of course, very, very important. If you get this wrong, then why spend all this time, right? We also did deployment testing with Bosch, because Bosch is an interesting system that does things in its own way. And if your data service doesn't comply with that, well, that's too bad. You cannot be deployed to Cloud Foundry. And if you are a Pivotal project and you cannot be deployed to Cloud Foundry, then why the hell do you even exist? Lastly, we are going to work on a formal logic, a temporal logic spec that, again, a machine can verify. That's pretty nerdy stuff. I'm not going to touch on that. So to summarize, RabbitMQ Queue Mirroring has issues. Yes, we know that. And Raft covers a similar space. It provides you a much more predictable recovery strategy and improved parallelism. This new design has a lot of, it's very promising. There are many improvements. We will see how it works out in practice. But implements in Raft, it's not really trivial. There are many, many decisions you have to make. And depending on what kind of system you're building, you may have to deviate, even though Raft really tries to cater to implementers and avoid the Paxos, 50 different flavors kind of Cambrian explosion. So yeah, our Raft implementation will be open source soon, and we are still learning about what it takes to implement it, where to adopt it. But like I said, we can adopt it incrementally, which is very good, meaning we won't have to wait till the 4.0 Big Bang release. Some of the improvements, especially around plugins, can be shipped earlier, which is great. So before we open up for questions, another announcement. It doesn't involve Raft, unfortunately, but might be interesting to the audience. RabbitMQ 3.7 shipped just a few days ago. So the general theme is it's automation and operator friendly. It has things such as peer discovery, which we previously had as a plugin. So if you run it on Kubernetes, or using a local config with Bosch, or an AWS using auto-scaling groups or EC2 instance tags, RabbitMQ nodes will just discover each other. It works pretty well. We have a distributed management plugin, so each node stores its own stats instead of a single node handling stats for every single cluster node, which means StatsDB overload is a thing of the past. It has a new config format, so it's an E style, so it's much easier to generate and much easier to present to human beings who are not familiar with Erlang, right? The Erlang format is still around if you need to. And in fact, in some areas, you still have to use it. But I think for the 80% of cases, it's just your ini, toml, that kind of format. It has a bunch of operator-oriented improvements, like you can specify certain limits on a per vhost basis. Operators can override policies for certain queue properties. It has internal improvements like improved message store concurrency. You can take a look at the changelog, but one important thing is that it is distributed using Bintray, Package Cloud, and GitHub. You will not find 3.7 in RabbitMQ.com, because honestly, those services do a much better job of distributing artifacts than we possibly can. Yeah, and with that, thank you very much for coming, and let's open up for questions.
Let's go ahead.
So, how do you test train splits, and what is your chaos monkey when you hammering the whole stuff into pieces?
Okay, so we're not quite at that level where we actually are able to do that, but it is our aim to pick up the Jepsen suite at some point and look at how it's doing stuff, or maybe if we can amend that to run it. But we're quite far off that, because it's kind of what's there at the moment is very much aimed at RabbitMQ. At the moment, we've got something that is RabbitMQ-like, which we perform all our testing. So yeah, that's.
I would add that the way we are going to test network splits is not very novel, probably IP tables and so on. But we're working on implements in Raft at the moment, not integrating Raft into RabbitMQ. And the way we test it is you develop a small app, deploy it with Bosch, and then kill something manually and see how it recovers. So it's not very automated at the moment, but again, once we have a Raft implementation that we're happy with and begin integrating, then we will actually use Chaos Monkey, because honestly, why reinvent that? And that kind of thing.
Yeah, I mean, one thing that we are doing on the more integration and the unit testing level is that we're using Erlang supports, have a very good support for kind of dynamic mocking. So we can do dynamic mocking to drop messages one way and not the other, and that kind of thing. So Erlang does provide us with the appropriate sort of plugin points to really muck around with, with what gets delivered and what doesn't.
Any other questions?
Wow.
I'm not sure if this is addressed by the change in the protocol. Versus in the cluster partitioning algorithm, there's a use case where a VM could be preempted and put to sleep. And so the rest of the cluster determines and detects that it's gone and decides that it's in the minority and stops talking to it. And when VM wakes up, it didn't know it was asleep, so it still thinks it's part of the cluster, and that does not recover, does not restart it, so you have a perpetual cluster partition going on. Is that still
Should I answer this?
Well, yeah, you can go. I've got
So
something to add
with
as well.
Raft, all those partition handling strategies go away because Raft dictates how you recover. And good riddance, right? No one likes that stuff. So in your case, if a VM is hibernated and then brought back up, or vmotioned to another host, which is the same thing just for a shorter period of time, Raft failure detection is timeout based, like in most systems. So if it happened in that period of time that is considered to be an outage, then it's an outage. But as we demonstrated, Raft can, in some cases, do nothing. And because there will be only one partition handling case, which is presumably if you can detect that you were a member of this cluster, you just rejoin and catch up. Raft, again, explains how that works. And if you, for some reason, are no longer a member of the cluster, well, that's too bad. Something should kill you and recreate, like Bosch. So I think the entire problem is not, it doesn't completely go away, right? We don't change the way TCP/IP works. Or a failure detection distributed systems, but it becomes radically simpler because there is only one failure handling mode. And it is described in Raft and it works for other systems. Honestly, we think that it's very straightforward. There really isn't, it's not particularly clever. Whereas what we do with our existing partition handling strategies, it's pretty smart.
Yeah, so I think the main key thing that it won't be doing is trying to change the topology. It just assumes the topology is still the same, but there's just one node that's not doing anything, right? So as long as you've got a quorum, you can still have availability. And if you had leaders on that node that was preempted, they would be re-elected on one of the available nodes. So currently, well, I didn't go into detail with this, but the thing that we rely on at the moment is distributed Erlang failure handling, which is quite relatively failure detection, which is quite primitive. And when that happens, we kind of try to reform things. And yeah, we're not going to do any of that. We're going to do less. So hopefully doing less will result in more stability in those cases.
I'd like to add maybe one more thing. So if your node fails and then recovers, at the moment in RabbitMQ, you have to resync the entire thing, right? We mentioned that. With Raft, it has a recovery mechanism that basically allows this failed node to say, hey, I'm up to this point in the log. Can you please give me just the rest? And that significantly shortens the period of time it takes to recover. Yeah. So that's another thing which does not directly address the problem that you're describing, but it helps operators.
There's no reset and there's no trying to get busy, that kind of thing. Any other questions? We welcome questions, generic question, RabbitMQ as well, if you have any. Maybe
in the hallway. Let's handle those in the hallway.
Okay.
Do you think Erlang makes it easier to implement Raft compared to you need to choose any other language?
So, right, I've implemented Raft in .NET, and it was a lot harder. Yes. So yes, I would say Erlang makes it a lot easier to implement it.
Why?
Well, firstly, you don't have to worry about any of the networking stack because Erlang kind of handles that transparently for you. You also got its concurrency model, which is very helpful. I mean, you can get similar things in .NET, of course, but and other framework, other runtimes. But yeah, for me, having done it twice, I found it a lot more pleasant and easy in Erlang.
Any other questions? Don't be shy.
Okay.
It just occurred to me for the very first time, sadly, as we were describing how the messages destined to multiple queues and the queues may be residing on different nodes. And so when the queues reside on multiple nodes, if the queues reside on the same node, there is an opportunity to keep only one copy of the message and attribute it to multiple queues.
We already do that, actually.
That's already done.
I forget what that is called.
Yeah.
Delegates.
And if the queues are on multiple nodes, do the messages have to be, do the copies of the message have to be created? Or is
That's what we want to achieve.
No, to some extent, that's how it's already works. So the way it does, say you have 3 nodes, and node A handles the request, and it needs to be routed to B and C, but B only has 1 queue and C has 5, right? It is sufficient to deliver 1 copy to B and 1 copy to C, and the rest happens in the runtime, right? So it's drastically less expensive. RabbitMQ has a mechanism called delegates, which does that. But due to the way chain replication works, you still get excessive traffic. So yeah, RabbitMQ will, there is a mechanism that will deliver, that the channels will use to deliver only 1 copy to each node. Unfortunately, that other parts of the system multiply traffic to the extent that Raft wouldn't.
So when you deliver to queues, we make a saving there, so it only travels to each node once. But when those queues then deliver the message to the consumers, they might cross the network again because they don't synchronize, and try to send the message all at once because you don't know when it's going to get consumed.
This delegate mechanism works between the node, let's call it the coordinator, for the lack of a better term, that the client is connected to, and queue masters. And what Karl described is what happens between queue masters and queue mirrors.
So in this regard, would it be advantageous, and in the HA situation, there is probably very little control, but outside the HA situation, where queue is not near it, would it be advantageous to make sure that the queues to which the messages send out are all located on a single node?
Possibly, but then you run into the problem of too many queues on a single node, basically, which is problematic, maybe more problematic, to be honest. But Raft doesn't really change that.
Well, you asked if there are any changes.
Okay, fair enough. I'm just mentioning that this Raft doesn't change everything, fortunately.
Just occurred to me for the very first time as I was going through this, that there is the question of message duplication is subject to also where the queues are on the same node or multiple nodes.
That's right. Yeah. So when you consume, if you connect to if you consume from a queue and that queue is the queue master is on the same node as you're connecting to, then you have that queue locality where you won't receive that additional copy. But if it's remote, then it will need to be copied first to the node you're on and then delivered. Yeah. That's the way it works at the moment.
From general capacity planning, we should assume the worst case scenario, if there is a 1 kilobyte message and it's sent out to 10 queues, then there should be 10 kilobytes of space, disk or RAM available across all nodes.
So when queues are co-located on a node, there will only be one copy of the message stored because there's already got a message store, but it's local to each node. So on disk, you don't have to do that. And when we're delivering to queues, there's also that efficiency gain that we get from the delegate, where only a single message across the network. But it's more about the consumption, I think, that you want to sort of try to plan around. Yeah.
Right. Any other Raft questions? We are happy to continue answering questions in the hallway.
Yeah.
Okay. It will be on GitHub later today, yes. We need to click some buttons on GitHub and write a new README.
Yeah. Just need to tweak it a little bit and then we'll get it out. Oh, okay, yeah. No, it will be under our organization pretty shortly. Okay.
Right. Thank you very much.
Thank you.